Cool guys, so today we are going to study Mohs algorithm. We had a previous lecture on square decomposition. It would be great if you have already gone through that, but even if you haven't, there's not much to worry about. So let's get started with Mohs. So let's firstly try to understand what kind of problems can we solve with Mohs, right? So Mohs algorithm can be used for query kind of operations or operations wherein I have no updates, right? Just queries. Updates can also be incorporated by using the method, but today we are gonna just talk about queries, right? So query could be something like for the range L to R, for all the elements in the range L to R, form some do some operation and return me the result and whatever the output is. And this is something I want, right? So for this kind of things, you can use Mohs algorithm, but on top of that, there's a condition on this. So the condition is that the queries should not be dependent on each other, or you should do a offline query. Now, what does this term offline or online means? Offline and then online, right? What do these two terms mean? So let's say I give you a couple of queries, Q1, Q2, Q3, Q4, right? And then I ask you the results. So there are two ways of doing it. So one way is that, okay, you'll compute for Q1, give me the result, compute for Q2, give me the result, compute for Q3, and then Q4, and keep giving me the result. The other way is that you'll say that, okay, I have these four queries. I can process them, but I'll process them in a different order, right? So maybe I want to calculate Q2 first, and then maybe like Q4, and then Q3, and then Q1, or any other such order. And then I'll return you the result. And obviously, I know that the result should be returned in the right order. So so let's say this had a answer O1, this had O3, this had O4, this had O2. So when I'll return you the answer, I'll definitely return O1, O2, O3, O4. That is similar to the way in which I got the queries, right? So if I'm able to do this kind of operation wherein I can select the sequence in which I'm gonna process the queries, then I'm gonna call it offline. And if I'm not able to do this kind of queries, right, then I'm gonna call it online. Now, when would queries actually be online? Queries would become online when they're dependent on one another. A very very trivial example here would be, for example, I am asking you that, okay, this is the function L to R. What you have to do is that you have to return me the sum from L to R, and at the same time you have to increment all the values in L to R by 1, right? Now this is one kind of query wherein you cannot use an offline operation, because as soon as you try to turn them offline, issues arise, because technically when you do Q0 or Q1, right, it would update the elements L to R, L1 to R1, right? And when you will do Q2, it will update the elements in L2 to R2. But since elements L1 to R1 has already been changed, Q2 should know about it, right? So you have to follow this particular sequence. If you're following this particular sequence, then it's online, else it's offline. Any doubts so far? All good? All right, let's proceed ahead. Cool. So the first thing is that most can be performed if I can, turn it offline. And what's the other thing about Moz? So Moz has a time complexity of n root n, where I'm considering that, okay, you can say q root q. I'm just considering that the number of queries you are going to perform is somewhere equal to n, or the number of elements. So you can say it's n root n or q root q, whatever way you want it to be. On the other hand, using something like a segment tree would actually give you n log n, right? So why Moz? The simple reason is that there are several problems which cannot be solved with segment trees, but they can be solved with Mohs algorithm. And Mohs algorithm is also simple to use. So hence we'll be studying Mohs. Now comes the point, what's the very fundamental unit of Mohs and how does this even work? So Mohs says that I'm gonna divide my entire array. So I'm considering that your operations or whatever like range queries you are trying to perform is somewhat for array elements. You can extend it for trees or for other data structures, but right now I'm considering array elements, right? And you are always going to perform ask for a query L to R, right? So Most says that, okay, we can do that, but first of all, let's say the array itself is divided into some buckets, smaller buckets, each of size root n, right? And obviously, since each bucket has a size root n, there would be total of root n buckets, right? Root n buckets, each of size root n. Now it says that once you have all the queries, let's try to sort them. Someone's mic is up. All right. Yeah, cool. That was a great voice, but whose mic is up? So now I know how he's a LGM. Basically, has a pretty good typing speed. Anyway, cool. Let's get back over here. Cool. So, what I'm gonna say is that okay, each of those blocks should be broken into root in, right? And when you are gonna process the queries, so I gave you all the queries Q1, Q2, Q3, and then I said that okay, I'm gonna do like process them offline, right? So you can do some operation on this, or basically you can then sort them up. But for sorting, we obviously know that for sorting you need a key, right? And in most of the times I'll say that okay, if let's say if my element is less than the element, if my element 1 is less than element 2, keep element 1 first and then element 2, right? But over here, since we are talking of queries, we are going to provide two keys, right? So the first would be the index of the block. Now what's block over here? Block is basically the bucket we talked of, right? So this block, this bucket would be having an index 0, this bucket would be having an index 1, this would be having an index 2, this would have an index 3, so on and so forth, right? So we'll say that if you have two queries, q1, q2, and it has the values L1 and R1, it has the values L2 and R2, then I'm not really concerned about L1, but I'm concerned about where this query, where the block starts itself, right? Now, a very easy way of coming out, like coming up with the starting point of the block would be to divide it by the root n or root size. This is something that we already studied in square root decomposition video, and hence that was helpful. And similarly over here, you can say L2 by root size 2. Basically, these are the blocks where this L1 or L2 would lie, right? So let's call them BL2 and BL1, right? Now I'll say that if my BL1 is less than BL2, then Q1 is gonna come before Q2, right? But in another case, if my BL1 is equal to BL2, in that case, R1 and R2 are gonna become important, right? Because that's the distinguishing factor now. So I'll say that if my BL1 is not equal to BL2, then just return me whatever element is smaller, else you return me if my R1 is less than R2, right? Now let's look at a small mathematical proof that if we are doing it this way, then how much can the total complexity become? So we are saying that okay, we are having these blocks. Let's just reuse the space, right? So what could be the worst case? Let's try to figure out some worst cases over here. So I can say that okay, every like I'll try to traverse the entire array for each of these blocks, right? So for the very zeroth block, let's say I'm having only two queries, LR, and my R for the zeroth block for the first query is, let's say, maybe like, let's say this element over here is A and this is B, right? So my R is A, R1 is A, and then for the R2 it's B, right? So the very first block I'm gonna draw would be starting from here, would go all the way up till here, right? And then I'll see that okay, I'm gonna go for Q2 right now, but right now I only have the knowledge for this particular block. So I'll have to traverse all the other elements that are remaining, right? So I'm gonna traverse from here till here. So technically it's order of n, right? So it added order of n in my case, right? Similarly for the first block, I'll add order of n. Similarly for the third block and for the last block also order of n. So how many blocks do I have in total? In total, I have root n blocks, right? And for each of the blocks, I'm having order of n operations. So my total complexity becomes n root n, right? What could be the other case? Like let's think of other extremity. Other extremity could be that I am having n number of queries in a single block itself, right? Or all the queries lie in the single block itself. Even in that case, the traversal to the right hand side would be actually limited by n, right? And you are having n queries over for this, right? So in total, you are just making n traversal along this line. So still your complexity actually remains order of n, not even order of n root n. Hence, the worst case time complexity over here becomes order of n root n. and you can't do worse than. How do we even use it? I already told you that okay, we are gonna sort it based on the block indexes, but how do we further use it? So I'm gonna say that okay, you have initially you have two pointers, L and R. Let's say L is your L is your left pointer and R is your right pointer, and let's give them some invalid values. So L is equal to 0 and R is equal to -1, just so that right now I'm not uh, considering even a single element of the entire array. Now, when I get a query Q, which I've already sorted, and when I'm trying to process it, it would be having a L1 and it would be having a R1, right? So the simple operation is that while my L1 is less than L, that basically means my left should be shifted to the left. I'll keep decreasing my L, right? Or while my L1 is greater than L, in that case I have to increase my L. Or while my R1 is less than R, I'll keep decreasing my R. Or while my R1 is greater than R, I'll keep increasing my R. So basically, I just want that my L and R should actually point to the values that are given over here, right? This is what I'm gonna do. But along with that, now I'm just increasing the values, right? So whenever I decrease the value of L, so I say that okay, my L should decrease. That basically means if my L is decreasing, right, then my range is actually increasing because this is the range L to R. And if I'm decreasing my L, some more elements are gonna get added, right? So in each iteration or in each operation, one element extra is gonna get added. Now I have to have some method, let's call it add. Let's keep it abstract for now. I'm not talking of the internal implementation, but yes, there has to be an element added whenever I do a L minus minus or I move my L to left. Now let's say there's some operation add that is called. Okay, let's just call add. Similarly over here, since I'm moving my left window to the right or left boundary to the right, there's some remove operation to be performed, right? Similarly over here, there's some remove operation to be performed, and over here there's some add operation to be performed. And that's pretty much Mohs algorithm for you. Now, how do we code it up? Code the remove or the add operations? They would actually depend on the kind of problems you are doing, and they could have completely different implementations. But for the sake of this particular session, we are going to solve a problem that was from AdCoder, and yeah, this is the problem. That is uh, range pairing query. Now this is a 600 level problem and AdCoder G. I'm not sure if you are familiar with AdCoder, but if you are able to do G, probably you'll score like top 5 or top 10 ranks in India. So yeah, a pretty hard problem I'd say, but it's still pretty easy if you know Mohs algorithm. Yeah, without knowing Mohs algorithm, it might even seem impossible. But knowing Mohs algorithm, it becomes really simple. So let's try to do this. The problem simply is that n people numbered from 1 to n are standing in a row, and the person I has color AI. And then there are q queries that we need to process, right? And in each query, you are given two integers, L and R, and we have to tell that if we are only considering the people in the range from L to R, then how many pairs of people would be wearing the same color of hat? Now let's try to understand if there was no L and R, how we could have done it. So problem simply states that number of pairs of people wearing same color, right? If there were no queries per se, you could have said that okay, for the entire range, I'll just calculate for each color how many people are wearing them. And let's say A was being born by X people, B was being born by Y people, and so on and so forth. So at most, X by 2 pairs can be formed by it, floor operation, and Y by 2 pairs can be born by it, right? And similarly, there would be some more values. Let's say some Z, so Z by 2, right? And then we have to just sum it up. Cool. So X by 2, Y by 2, Z by 2 can actually be done. Now what I'm gonna say is that if I know this information, and this I can say only by traversing the entire array, right? If I can come up with this by traversing the entire array, so if I use the Mohs algorithm for each query over here, then my overall complexity would be order of n root n as we studied before. Now would order of n root n suffice over here? Let's just look at the constraints for that. So the constraints over here is n is less than or equal to 10 to power 9, right? And even q is less than or equal to 10 to power 6. So n root n should fit over here. So let's try to code it up. And I'm gonna start from a scratch from scratch over here, and then maybe we'll just copy some of the code from here so that you also understand how to use black box views and how to just code up your solution when required. So let's just copy maybe this part, right? So I'm gonna copy this part. This is just from CP algorithms, square root decomposition section, and over here they are talking about the Mohs algorithm implementation. You can technically copy it from every website, but this is one of the most trusted websites, so hence I'm copying it from here. So over here, over like above it, they have given the query, or this is the struct query. So basically, you get the fields that should be in a query, and obviously a query consists of a L and a R and an index. So nothing surprising over there. Let's cut this particular part. This is the internal implementation. This is somewhat similar to what I told you, that you'll start from L equal to 0 and R equal to -1. And for each of the queries, you'll try to increment or decrement your L and R depending on the constraints. And each time you do that, so if you are increasing the size of the window, then you're going to add that particular element. If you are decreasing the size of the window, then you're going to remove that particular element. So let's copy this up. Rather, let's just copy this entire thing up, right? And let me just paste that in here. All right. So now what format is the question given to us? So initially we are given an n, that is fine. So n we are taking, and then we are taking our entire v, right? And then it's giving us q. So let's say q, or the number of queries. Okay, cnq. Fair enough. Let's call this res, and this would be also size q, because the result that you're gonna return would also be the size be of the size of the queries. Now what I'm gonna say is that let me declare a vector of type queries itself, right? And let's name it queries, and for int I in q I plus plus, I'm gonna take two inputs from the user, that is L and R. And since we are talking of zero-based indexing, let's reduce one from them. Once I have these values, let's just store them into queries, right? Okay, so let me instantiate object query qr dot L equal to L, qr dot R equal to R, and qr index is equal to I, right? That sounds good. And now let's push that particular qr object to my queries. So I'm gonna say queries dot push back qr, right? Once done this, as we said that okay, we have to sort it. So I'll sort this entire array or vector, and then obviously I'll get over here and I can do this. But over here I'm getting a squiggle that this have not been implemented, right? So let's look in them. So firstly, we have a remove operation and an add operation which we have to implement. But what can I do over here? Now I said that I can have a result, right? And I can have an unordered map. Basically, whenever I'm adding something, right? So I'm adding something, and yeah, sure, that the vector I was taking can be initialized over here so that it is accessible to those elements as well. So instead of doing it over here, I can just say n0. Cool. So that being said, if I'm removing a particular index, I have to say that this index is being removed, right? So this value is being reduced by 1, and if my okay, that to be int index, okay, and if this value is now odd, right? If this value is odd, that basically means it was even before, right? So if it was even, it was adding on to a particular pair, and now that pair is being removed. So let's reduce our result. Or when we are adding it, so we have to do the exact opposite thing. So over here we can say that okay, this particular value, whatever it is, which I'm not have no clue about, it's gonna increase, right? And if the value is now even, then it's gonna add to a particular pair, so my result is gonna increase. And when I'm trying to fetch the values, I'm just gonna return this. And yeah, that pretty much seems fine to me. Let's try to understand if we are missing something. Yeah, block size also needs to be uh, initialized, and block size, as we said, is just square root n plus 1. And I think we should be good with this. Let's just have a look. Okay, we were doing this wrong. Yep. Cool. So yeah, that's how it works. So mostly straightforward. Like even when I was doing it, I just copy pasted the entire block or code snippet from CP algos and just try to implement the relevant functions. In my case, those were the remove function and the add functions. Or in all the cases, they are gonna be the remove function or the add function, but the implementation could be totally different. That depends on the problem. So once you have coded this thing up, rest of the entire structure should remain same, and you would be able to solve some complicated problems even like this one.